Today we are going to look at system design for rate limiter. A rate limiter, as the name suggests, puts a limit on the number of requests a service fulfills. It throttles requests that cross the predefined limit. For example, a client using a particular service API that is configured to allow 500 requests per minute would block further incoming requests for the client if the number of requests the client makes exceeds that limit. Now, why do we need a rate limiter? The primary reasons would be preventing resource starvation, managing policies and quotas, controlling data flow, and avoiding excess costs. So here's what it looks like pictorically. So there's a client, it sends request, there's a rate limiter. Rate limiter, has its rate limiting logic, and if the logic, allows the request, then it goes through the API servers, the request gets processed, and the response is returned. So to summarize the requirements, first, accurately limit excessive request. Second, low latency. Third, it should use as little memory as possible. Fourth, it should work in distributed environment setting. That is, the rate limiter can be shared across multiple servers or processes. Then exception handling. We should show clear exceptions to users when their requests are throttled. Then high fault tolerance. If there are any problems with the rate limiter, it does not affect the entire system. Now, where we should put the rate limiter? While designing a rate limiter, an important question to ask ourselves is, where should the rate limiter be implemented? On the server side, in the gateway? Well, there's no absolute answer. It depends on your company's current technology stack, engineering resources, priorities, goals, etc. Here are a few general guidelines. First, you should evaluate your current technology stack, such as programming language, cache service, etc., to make sure your current programming language is efficient to implement rate limiting on the server side. Second, identify the rate limiting algorithm that fits your business need. When you implement everything on the server side, you have full control of the algorithm. However, your choice might be limited if you use a third-party gateway. Third, if you have already used microservice architecture and included an API gateway in the design to perform authentication, IP whitelisting, etc., you may add a rate limiter to the API gateway. Then the last one would be building your own rate limiting service takes time. If you do not have enough engineering resources to implement a rate limiter, a commercial API gateway is a better option. So here are a few algorithms for rate limiting. Token bucket, leaky bucket, fixed window counter, sliding window log, and sliding window counter. So let's look at all of these one by one. So token bucket algorithm. The token bucket algorithm is widely used for rate limiting. It is simple, well understood, and commonly used by internet companies. Many companies like Stripe use this algorithm to throttle their API requests. The token bucket algorithm works as follows. A token bucket is a container that has a predefined capacity. Tokens are put in the bucket at preset rates periodically. Once the bucket is full, that is, no more tokens are added. As in the figure, the token bucket capacity is 4. The refiller puts 2 tokens into the bucket every second, and once the bucket is full, extra tokens will overflow. So pretty simple. Now in the token bucket algorithm, each request consumes 1 token. When a request arrives, we check if there are enough tokens in the bucket. So the following figure shows how it works. If there are enough tokens, we take 1 token out of each request and the request goes through. If there are not enough tokens, the request is dropped. So as you can see in the figure from the left hand side, you have a bunch of requests. It comes through, we check if there are enough tokens. If not, we drop the request, otherwise the request goes through. So the token bucket algorithm takes 2 parameters. The bucket size, that is the maximum number of tokens allowed in the bucket. The second is refill rate, the number of tokens put in the bucket every second. Now, how many buckets do we need? This varies, and it depends on the rate limiting rules. Here are a few examples. It is usually necessary to have different buckets for different API endpoints. For example, if a user is allowed to make 1 post per second and add 150 friends per day and like 5 posts per second, 3 buckets are required for each user. If you need to throttle requests based on IP addresses, each IP address requires a bucket. If the system allows a maximum of 10,000 requests per second, it makes sense to have a global bucket shared by all requests. So what are the pros and cons of token bucket algorithm? The pros would be the algorithm is easy to implement, it's memory efficient, token bucket allows a burst of traffic for short periods, a request can go through as long as there are tokens left. The cons would be 2 parameters in the algorithm are bucket size and token refill rate. However, it might be challenging to tune them properly. Now let's look at leaky bucket algorithm. The leaky bucket algorithm is similar to the token bucket, except that requests are processed at a fixed rate. It is usually implemented with a first in, first out queue. The algorithm works as follows. When a request arrives, the system checks if the queue is full. If it is not full, the request is added to the queue. Otherwise, the request is stopped. Requests are pulled from the queue and processed at regular intervals. So as you can see in the figure, you have request on the left hand side. It comes across to the token bucket algorithm, the leaky bucket algorithm, and it checks whether the bucket is full or not. If it is full, then the requests are dropped. If not, it is added to the queue, and then from the right hand side, it is processed at a fixed rate. So leaky bucket algorithm takes the following two parameters: bucket size, which is equal to the queue size. The queue holds the request to be processed at a fixed rate. Outflow rate, it defines how many requests can be processed at a fixed rate, usually in seconds. Shopify, an e-commerce company, uses leaky buckets for rate limiting. The pros would be memory efficient given the limited queue size. Requests are processed at a fixed rate. Therefore, it is suitable for use cases with a stable outflow where stable outflow rate is required. The cons would be a burst of traffic fills up the queue with old requests, and if they are not processed in time, recent requests will be rate limited. There are two parameters in the algorithm, and it might not be easy to tune them properly. Now let's look at fixed window counter algorithm. Fixed window counter algorithm works as follows. The algorithm divides the timeline into fixed time windows and assigns a counter for each window. Each request increments the counter by 1. Once the counter reaches a predefined threshold, new requests are dropped until a new time window starts. So let's use a concrete example to see how it works. In the figure below, the time unit is 1 second and the system allows a maximum of 3 requests per second. In each second window, if more than 3 requests are received, extra requests are dropped. A major problem with this algorithm is that a burst of traffic at the edge of the time windows could cause more requests than allowed quota to go through. Consider the following case. So in the figure below, the system allows a maximum of 5 requests per minute, and the available quota resets at the human-friendly round minute. As seen, there are 5 requests between 2 o'clock and 2:01, and 5 more requests between 2:01 and 2:02. For the 1 minute window between 2 o'clock and 30 seconds and 2 o'clock and 1:30 seconds, 10 requests go through, which is twice as many as requests allowed per minute. So the pros and cons would be, the pros would be it's memory efficient, it's easy to understand, resetting available quota at the end of the time unit fits certain use cases. The cons would be spike in traffic at the edges of the window could cause more requests than the allowed quota to go through. Let's look at sliding window log algorithm now. As discussed previously, the fixed window counter algorithm has one major issue. It allows more requests to go through at the edges of the window. The sliding window log algorithm fixes the issue, and it works as follows. The algorithm keeps track of request timestamps. A timestamp data is usually kept in cache, such as sorted set of radius. When a new request comes in, remove all the outdated timestamps. Outdated timestamps are defined as those older than the start of the current time window. Add timestamp of the new request to the log, and if the log size is the same or lower than the allowed count, a request is accepted. Otherwise, it is rejected. So let's look at an example. The rate limit. So here the rate limiter allows 2 requests per minute. Usually the Linux timestamps are stored in the log. However, human readable representation of time is used in our example for better readability. The log is empty when a new request arrives at 1 o'clock 1 seconds. Then the request is allowed. The new request arrives at 1 o'clock 30 seconds. The timestamp is 1 o'clock 30 seconds is inserted in the log. After the insertion, the log size is 2, not larger than the allowed count, and the request is allowed. A new request arrives at 1 o'clock 50th seconds, and the timestamp is inserted into the log. After the insertion, the log size is 3, larger than the allowed size 2. Therefore, this request is rejected even though the timestamp remains in the log. A new request arrives at 1 o'clock 1:01 and then 40 seconds. The request in the range 1 o'clock 40th second to 1 o'clock 1 minute 40th seconds are within the latest time frame, but requests sent before 1 o'clock 40th seconds are outdated. 2 outdated timestamps 1 o'clock 1 second, 1 o'clock 30 seconds are removed from the log. After the remove operation, the log size becomes 2 and therefore the request is accepted. Now let's look at sliding window counter algorithm. This algorithm is a hybrid approach that combines the fixed window counter and sliding window log. The algorithm can be implemented by 2 different approaches, and the following figure shows how this works. So assuming the rate limiter allows a maximum of 7 requests per minute and there are 5 requests in the previous minute and 3 in the current minute, for a new request that arrives at a 30% position in the current minute, the number of requests in the rolling window is calculated using the following formula. Request in the current window plus the request in the previous window and multiplied by overlap percentage of the rolling window and the previous window, we get 3 plus 5 into 70%, which is equal to 6.5 requests. Depending on the use cases, the number can be rounded up or down, and in our example, it is rounded down to 6. Since the rate limiter allows a maximum of 7 requests per minute, the current request can go through. However, the rate limiting can be reached after receiving 1 more request. The pros of this approach would be it smoothes out the spikes in traffic because the rate is based on the average rate of the previous window, and it's memory efficient. Cons: it only works for not so strict look-back window. It is an approximation of the actual rate because it assumes requests in the previous window are evenly distributed. However, this problem may not be as bad as it seems. According to the experiments done by Cloudflare, only 0.003% of requests are wrongly allowed or rate limited among 400 million requests. So now let's discuss high-level architecture. The basic idea of rate limiting algorithms is simple. At the high level, we need a counter to keep track of how many requests are sent from the same user, IP addresses, etc. If the counter is larger than the limit, the request is disallowed. Where shall we store counters? Using the database is not a good idea due to the slowness of disk access. In-memory cache is chosen because it is fast and supports time-based expiration strategy. For instance, Redis is a popular option for implementing rate limiting. It's an in-memory store that offers two commands, increment and expire. Increment, which increases the store counter by 1. Expire, it sets a timeout for the counter. If the timeout expires, the counter is automatically deleted. So as you can see in the figure, so you have a client, you have a rate limiting middleware, and it contacts Redis, and if the response is positive, it contacts its API servers. And the flow can be described as follows. The client sends a request to the rate limiting middleware. Rate limiting middleware fetches the counter from the corresponding bucket in Redis and checks if the limit is reached or not. If the limit is reached, the request is rejected. If the limit is not reached, the request is sent to API servers. Meanwhile, the system increments the counter and saves it back to Redis. What if the rate limit gets exceeded? In case a request is rate limited, API returns a HTTP response of 429, that is too many requests to the client. Depending on the use case, we may enqueue the rate limited request to be processed later. For example, if some orders are rate limited due to system overload, we may keep those orders to be processed later. This section talks about the rate limiting headers. For example, how does a client know whether it is being throttled? How does a client know, the number of allowed remaining requests before being throttled? The answer lies in the HTTP response headers. The rate limiter returns the following HTTP headers to the client. X-rate limit-remaining, that is the remaining number of allowed requests within the window. Then X-rate limit, it indicates how many calls the client can make per time window. And X-rate limit-retry-after, that is the number of seconds to wait until you can make a request again without being throttled. So expanding on the architecture, rules are stored on disk. Workers frequently pull rules from the disk and store them in cache. When the client sends a request to the server, the request is sent to the rate limiting middleware first. Rate limiter middleware loads rules from the cache. It fetches counters and last request timestamp from Redis cache. Based on the response, the rate limiter decides if the request is rate limited or not. Then it is forwarded to API servers. If the request is rate limited, the rate limiter returns 429, that is too many requests to the client, and in the meantime, the request is either dropped or forwarded to the queue. So on the right hand side, you have the diagram. As you can see, there is a client, then there's a rate limiter middleware, and then if it is rate limited, then 429 status, that is too many requests, is sent back to the client. If it is not, then it goes to the API servers. Then you have cache rules, and you have workers which stores the rules. They fetch the rules from a persistent storage. They populate the cache, and that's how your rate limiting logic is kind of updated. And then on the rate limited side, if there are too many requests, then one option could be dropping the request. The other option could be putting them in a message queue to be processed later.